Hello, I'm Professor Rad, and this is Precalc video 2-12, Introduction to Rational Functions. So in our previous set of videos, we've been looking at polynomials, and polynomials are to functions what integers are to numbers. So they're like the basic building blocks that we'll be using for our algebraic functions moving forward. So once you have integers, you can start to form fractions out of them. So similarly, once we have polynomials, we can create fractions of them. And we're going to call those fractions rational expressions. So let's go through a few definitions for our rational functions, and then we'll apply these definitions to some examples. So I'm going to get out of the way in case you want to pause the video here and copy these definitions down. And here we go. So R of x is a rational function if R of x is equal to P of x over Q of x. So it looks like a nice fraction for polynomial functions P and Q. So we are fractions of polynomials. And of course, we don't want the denominator to be the zero function because then we can't divide and the function would explode or, something. Now, if the degree of the numerator is less than the degree of the denominator, then we're going to say R of x is a proper rational function, just like we would do with fractions. So if you have a fraction where the top is smaller than the bottom, then that's a proper fraction. Otherwise, it's going to be improper. So the way that we measure the size of polynomials is by the degree. So as long as the size of the numerator or the degree of the numerator is smaller than the size of the denominator, the degree of the denominator, then will be a proper rational function. If the degrees are the same, or if the degree of the numerator is larger than the degree of the denominator, then we have an improper rational function. And lastly, just like you can simplify a fraction, you can simplify a rational expression. So if P and Q have no common factors other than 1, because 1 is a common factor for all things, then the rational function is said to be in simplest form. And if they do have a common factor, then we'll cancel out that factor, but we will have to make sure we account for the canceled factor when we state our domain. So let's do a couple of examples of looking at a rational expression, then we'll simplify it, and we'll do things like we'll state its domain and maybe talk about the x and the y-intercepts a little bit. So let's do that first example together. For our first example, we're going to write this rational expression in simplest form, and then state the domain and its x and y-intercepts. And then we'll repeat that process for a second rational function, just so we can see a few different things that might happen. So for this rational function, well, for any rational function, if you're going to simplify it, you want to make sure you factor the numerator and the denominator. So remember, when you have fractions, you can cancel common factors in the top and the bottom. So that's what you're really doing, is you're canceling common factors when you say something like, well, to simplify 6/9, you divide the top and bottom by 3. What you're really doing is you're factoring out a 3 from the top and the bottom, dividing that out to get a 1, and then you're left with the remaining factors. So that's what we're going to do here. We have to factor the numerator, factor the denominator, and then we'll cancel out any common factors in order to simplify. So what's important when I look at this to start is that this 7 and this 28 can't interact at all, because the 7 and the 28 are not factors of the numerator or denominator, they are terms of the polynomials. So we need to have like those blobs. We need something times something, and we need those things that are being multiplied in the top and bottom to be the same if we're going to cancel them. So the numerator on this one is not too bad to factor. We need two numbers that multiply to -28 and add to 3. So that's going to be +7 and -4. So my numerator here will be x plus 7, x minus 4. For the denominator, it's not quite that easy because our leading coefficient is a 2. It's not a 1. So there are a few different strategies that can be used to factor this denominator. I'm going to use one that I know and I've become comfortable with. If you know an alternate technique that works well for you, feel free to use it, continue to use it. If you don't know a good technique, this is the one I know and use and like. So what I'm going to do is I'm going to multiply 2 times 7 to get 14. And then I'm going to look at this positive 15. These two numbers are going to guide me into splitting this trinomial up into 4 terms so that I can apply grouping to factor. So the way that I'm going to do that, I need 2 numbers that multiply to 14 and add to 15. So I think that 14 and 1 are going to do the trick. If I multiply 14 times 1, I get 14. And if I add 14 plus 1, I get 15. These 2 numbers tell me how to split up that middle term. So I can rewrite this as 2x squared plus 14x plus 1x, and then plus the 7. So what I've done is I've split this 15x up into 14x plus 1x. That's why in this process, we need them to add to 15 so we can split them up into those 2 pieces. The reason we want them to multiply to 14 is so that our grouping technique will work. So for example, if I look at these 2 terms, they have a 2x in common. So I can factor that out and get x plus 7. These 2 terms have nothing other than 1 in common. So I'm just going to write plus 1 times x plus 7. And now grouping is going to be effective if these 2 factors are the same, and they are. If we had chosen something other than 14 and 1, so if they didn't multiply to be 14, then this grouping would not work. But since it did work, we can factor that x plus 7 out. And then our other factor is the 2x plus 1. So this means our denominator is going to be x plus 7 and then 2x plus 1. I always like to take a breath after like a big factoring thing. So that's our factored form for our numerator and our denominator. So now if they have anything in common, we can cancel out those common factors. So in this case, they do have an x plus 7 in common. So we can factor that out. And this will give us x minus 4 over 2x plus 1. All right. Sorry, I thought I was going to sneeze there for a second. I think I contained it. So now that we are of this form, we're going to be done. So you may be tempted to say, but Professor Red, 2 is a factor here of 2x and 2 is a factor of 4. So can't we cancel those? No. So the reason we can't cancel with this 2x and this 4 is because the 4 up here is a term in the numerator because it's being subtracted from x. It's not a factor of the whole numerator. So if I had had 4 times x up here, like 4x, and if I had 2 parentheses x plus 1, then we would have a factor of 4 in the top and a factor of 2 in the bottom that could cancel. But the 2 here is only a factor of the 2x term. It's not also a factor of plus 1. And the minus 4 is a term in the top. So we can't cancel terms, we can only cancel factors. So we had this big thing in parentheses times this big thing in parentheses. So the parentheses things, these are our factors in the top and in the bottom. So this is going to be our function in simplest form. So for the first part, if I were to say in simplest form, we have x minus 4 over 2x plus 1. Okay. Then we need to state the domain and the x and y intercepts. So think back to when we found compositions of functions and we had more than just a final result to bear in mind when we looked at the domain. The same thing is going to be true with rational expressions, especially when we simplify them. So our original function had this as its denominator, which means our original function had a factor of x plus 7 in the denominator. So we need to take that into consideration when we go to find the domain. So in general, for the domain of a rational function, you want to set your denominator not equal to 0. And then typically we'll be doing some factoring to solve that. So if you already have it in factored form, you can look at it in the factored form, but before you simplify. Okay? So for the domain, make sure you look at the denominator before you simplify. So in this case, we're going to take this denominator here. So we have x plus 7 times 2x plus 1, and that cannot equal 0, because if the denominator is 0, then the fraction doesn't exist. And since we're in factored form, we'll use the 0 property and say x plus 7 can't be 0, and 2x plus 1 can't be 0. And then these are linear sorts of things, so we can solve this pretty easily. Just subtract 7, so x cannot be negative 7. And here we'll subtract 1, so 2x cannot be negative 1. And then we'll divide by 2, so x cannot be a negative 1/2. Now, especially when your denominators have a lot of factors or a lot of problem spots, then set builder notation is going to be easier for us in the long run. So I'm going to tend to use set builder notation for my rational expression domains. So for our domain, we have the set of all x, so that x is not negative 7, and it's not negative 1/2. Okay, so that's our domain for this rational function. This is different than the domain of if we had just started here. Because if we had just started here, 7 would be no problem. Negative 1/2 is still a problem, but negative 7 is a problem. In our original function, negative 7 was a problem. So we have to make sure we account for that in our domain. Lastly, to state the x and y-intercepts, now we're going to do that the normal way that we would find those. So to find your y-intercept, you substitute in 0 for x. And to find your x-intercept, you set the function equal to 0. So let's find our y-intercept first, because that one's usually a little bit easier. So for the y-intercept, we're going to find f of 0. And when I'm finding a y-intercept, I can use either the the original form, I can use the simplest form, or I can use this factored form. I'm going to use, in this case, the simplest form. However, you do want to be careful when you use your simplest form to check against your domain, in case your domain was like x can't be 0. But in this case, 0 is allowed. So we're going to substitute into here 0 minus 4 over 2 times 0 plus 1. So that'll give me negative 4 over 1, which is negative 4. Now, for my classes in particular, when we state intercepts, I like to distinguish an intercept from an equation, especially with rational functions, because we're going to have intercepts and asymptotes. So we'll be having points and equations. So when we state an intercept, let's make sure we state the coordinates of the intercept, not just the y or the x value. So for the y-intercept, I'm going to state the point 0, negative 4. Here we go. That's our y-intercept. To find the x-intercepts, we need to find when the function itself is equal to 0. Now, in this case, I do like to use the simplest form for this process so that I won't be tempted to find a value that is not in my domain. So I'm going to set my simplest form equal to 0. Now, in this case, when you have a rational expression equal to 0, if this equation is going to be true, that means the top has to be 0, right? Doesn't matter what the bottom is, so long as it's not 0, right? So we can't have -7 or -1/2 in the denominator, but the top can be whatever it wants to be as long as we don't have one of those things. So I'm just going to set the top equal to 0 because that's when this fraction will be 0. So x minus 4 is 0. So if we add 4, we get x equals 4. So this rational expression will only have one x-intercept, and it will be at 4, 0. Now, one of the other reasons, one of the other things I wanted to point out with this is if I had gone with this factored form, I could also have set the numerator equal to 0. So I would have x plus 7 is 0, x minus 4 is 0. We'd get our 4 from here, but now I'd have to be careful because if I used this factor, I'd get -7, which is forbidden from the domain. So that's why I like to use the simplest form when I go to find my x-intercepts. And if you want like just a shortcut, you just set the numerator equal to 0. But I always like to write this part so that I remember what I'm doing and why I'm doing it. And then the last thing, it didn't ask us for it on this problem, but I did want to point out that this rational function is not proper. So the reason this rational function is not a proper rational function is because the degree of the numerator and the degree of the denominator are the same. So because they're both like the same size, this would be like if you had the fraction 4/4. 4/4 is an improper fraction because it will reduce to a whole number. So the numerator is not smaller than the denominator. All right, let's do another example of this whole process so we can see what other fun stuff might happen with rational functions. For the second part of this example, we'll be looking at the rational function x minus 8 over x cubed plus 64. So for our first step, we want to write this rational function in simplest form. So if you want to try your hand at that and practice doing some factoring and reducing, you can pause the video here and work through that. Otherwise, I'm just going to walk through it like I did with the last one. So the good news is my numerator is a linear polynomial and my denominator is cubic. So there's nothing up top that I have to factor because the only common factor is 1 between x and 8. Also, this is a proper rational function because the degree of the top is smaller than the degree of the bottom. So this one would be an example of a proper rational function. So the only thing we have to factor is the denominator. Now, I happen to recognize the denominator as the sum of perfect cubes. So x cubed plus 64 is the same as x cubed plus 4 cubed. In our class, you are expected to recognize this form and know how to factor it. So let's talk about how to factor the sum of perfect cubes. So when you write it in this form, x cubed plus 4 cubed, your first factor is going to be a linear factor, and it looks just like this, but without the cubes. So we have x plus 4. The same thing would be true if we had x cubed minus 4 cubed. The first factor would be x minus 4. So this is our x plus 4. Our second factor is going to be a quadratic polynomial. So here's how we find that second factor. You take this first thing. Well, actually, I'm going to reference here. So you're going to take this first thing and you're going to square it. So x squared is x squared. I'm going to skip a little space for a minute, and I'm going to multiply these two. So x times 4 is 4x. I'm going to skip a little space, and you square this piece. So 4 squared is 16. This last term is always positive, and the sign here is the opposite of the sign here. So that's the process that I use to remember how to factor the sum of perfect cubes. So I write it as my perfect cubes, and I drop the cubes to get the first factor. Then I square the first, I multiply these two, I square the second. This on the end is always plus, and this one is the opposite sign of this one here. And if we were to multiply all of this out, we would indeed get x cubed plus 64 back again. So this rational function is going to be x minus 8 over x plus 4 times x squared minus 4x plus 16. Now, remember we had that theorem that says a polynomial in the real numbers can factor completely if into linear and prime quadratics. So we're still working in the land of real numbers here. We're not going to delve into complex when we talk about simplifying or we talk about the domain of a rational function. So we do need to check whether or not this quadratic is prime. One way to do that is to use your discriminant. If the discriminant is positive or 0, then it can be factored. If it's negative, it can't be. So let's just check that real quick. Remember the discriminant is b squared minus 4ac. So negative 4 squared is 16 minus 4 times 1, so 4 times 16 is 64. That's going to be negative. So the discriminant is negative, so that means we can't factor this. So this is as factored as it gets. And if you want to write the numerator in factored form, you can just put parentheses around the top, or if it helps you to remember, you can put a 1 there as well. So it looks like none of the factors cancel because the only one up top is an x minus 8, and we didn't get that in either of the factors for the bottom. So this function was already in simplest form. So for that first part in simplest form, you could give either answer. So you could give the answer x minus 8 over x cubed plus 64. That would be an acceptable answer. Or you could give it in factored form. So you could say x minus 8 over x plus 4 times x squared minus 4x plus 16. All right, so now let's state the domain. So I'm going to erase this piece over here. For the domain of this function, remember that the denominator cannot be 0, and we want to be looking at the original function or before we canceled any factors. So we didn't cancel any factors, so I'm going to use the factored form here. So we have x plus 4 times x squared minus 4x plus 16 cannot equal 0. So since we're in factored form, we set each factor not equal to 0. So x plus 4 can't be 0. And x squared minus 4x plus 16 can't be 0. Now I'm going to work through this problem the way that I often see students work through it. And then I'm going to talk about what's dangerous or what's not wrong, but also not totally nice either about this process. So left side's easier, so we'll do that one first. So I subtract 4 and I get that x cannot be negative 4. Now we have a quadratic here, which we can't factor, so we can always use the quadratic formula to solve. So x can't be negative b plus or minus the square root of b squared minus 4ac. We just found that, that was 64, all over 2a. So now I am going to simplify all these pieces. So let's see, 64 minus 16, so 48 over 2. Okay, let's see. Well, I know 16 is a perfect square that goes into 48 3 times. So we can't be 4 plus or minus 4i root 3 over 2. So I did a lot of steps there in one. So just to revise or go over how I found that, I got the I because there was a negative under the radical. So you can take out an I, just be careful, don't hurt yourself. So if you have a negative under the radical, that can turn into an I outside. And then 48 is the same as 16 times 3. So the square root of 16 is 4, and then the square root of 3 stays there. Then up top, I now have a common factor of 4. So I can factor that out to get 1 plus or minus I root 3 over 2. And because I factored out that 4 has a common factor with 2 of 2. So I can divide that out to get x cannot be 2 plus or minus I root 3. Oh, 2 times, what am I doing here? 2 times 1 plus or minus I root 3. A little overzealous, I think, here. There we are. Okay, so we found our domain. We used the beautiful quadratic formula. We had complex results. This is a little bit of agony. And the good news is we don't need to put ourselves through that agony. So here's why. For our domain, we're looking for our domain out of real numbers. As soon as you recognize that this factor has no real solutions, you don't have to go through this process because you're going to get a complex number and you're going to say, well, x can't be this complex number. Well, x couldn't be the complex number anyway. We're only looking for real numbers where it's going to break down. So the domain of this function is just this piece here. So it's the set of all x so that x cannot be -4. So again, it's not wrong to do this. It's not really wrong to include 2 times 1 plus minus I root 3 in your notation here. That's not wrong. It's just unnecessary work. And it's a place where you're likely to make some mistakes. And it's a tough process to do, right? So if we had had a quadratic that could factor, we would have factored it beforehand. So this process would have been easier. And if we had a quadratic with like irrational roots, then we would have found that with our quadratic formula and we would have needed to do it in that case. But often what I see students do is get confused by this I stuff. So I wanted to bring it up. All right, so that's our domain. Oh gosh. So let's find our x and our y-intercepts. For the y-intercept, I'm going to use this original function since it is much nicer looking than this one here. And I'm going to substitute in 0. So I plug 0 in for x, and I'll get 0 minus 8 over 0 cubed, which is 0, plus 64. So I get -8 over 64. And that will reduce to -1/8. So the coordinates of our y-intercept are 0, -1/8. And lastly, I think I left this teeny tiny space up here for us to do our x-intercepts. So for the x-intercepts, we can set the numerator of the simplest form equal to 0. So in this case, it already was in simplest form. So I'm going to set x minus 8 equal to 0, which means x is equal to 8. So the coordinates of our x-intercept are going to be 8, 0. Ta-da. Hooray! Okay, so it's a lot of work. Again, some of it, sometimes we do need to go to that quadratic formula. If we have irrational roots, if we have complex roots, then we don't need to take this approach. So use the quadratic formula wisely. Remember our factoring technique here for sum or difference of perfect cubes. So that can be a little bit tricky as well. That's going to wrap it up for this video in terms of what we're going to be, new concepts we'll be learning. In our next video, we are going to start looking at rational functions and figure out how we can figure out their asymptotes. So we looked at asymptotes graphically previously, and we've talked about them a little bit, but now we want to know, okay, if I have a rational function, how do I find a vertical asymptote or horizontal or maybe even oblique? So I look forward to seeing you in that next video. In the meantime, I hope this helped introduce you to rational expressions, and I hope you have a wonderful day. Bye for now.